Last lecture before the exam. But like I said, just now to get it on the recording, tomorrow night I will be reviewing for the exam. If it is inclement weather, which is the odds-on favorite according to Eli, then that is all we will do. If it's clear weather, we can't pass up going out to observe the sky, in which case it will be you guys pretending you're doing the lab final, but as a group. All right, so let's continue on pretty much where we left off. We saw this picture before. I talked about Hale-Bopp, the Heaven's Gate Colt. You remember it. So we're going to learn more about comets and meteor showers today. A few other things mixed in. Remember where the asteroids are. I left that in. You can see I left it in. It's got markings on already. Just so we can see where asteroids are. In a little bit, we'll see another slide that shows asteroids with their paths. And you might be a little concerned when we look at that. And that's the reason it's given. Different types of asteroids we talked about were the type C, which means that they had organic type compounds in silicate rock. Type S, which was just silicate rock. They say stony, but silicate is what it stands for. And then we have M for metallic. And I think I ended with this picture, didn't I? Boy, if it goes on anymore with picture, no. We started the right place. So I think we started the right place. This is a picture of a meteorite that was recovered, a metallic one. I'm a little bit worried. No, it's not. I don't think we did this. Okay. Asteroids have moons. You tend to think that only planets have moons, right? I mean, that's human to tend to think that only planets have moons. After all, we have a moon. That's most people's experience. And then when they start learning a little astronomy, they learn like, oh yeah. And Mars has, how many moons does Mars have? Mars has 2 moons, Phobos and Deimos, which would be, Phobia is fear, and Deimos is terror. They're like, the twin sons of somebody in mythology. Anyway, it's not just planets that have moons. So here we have the asteroids, Ida, and its moon, Dactyl. So Dactyl is the little fellow you see there. On the right is orbiting around with, now I say with because you have to have one much more mass than the other for it to make sense to say orbiting around. Otherwise, we're both orbiting together around the center of mass. And so it's interesting to note that not just planets can have moons. And obviously, in theory, a moon can have a moon. Like, what's the difference? The sun has planets going around it, and the planets have moons going around them. It's the same thing, just on a different scale, right? Here are the pictures of the moons of Mars. Now, I wouldn't know which one's which. I know they look different, but this one here is fear, and this one here is terror. Just so you know. Now, do those look like the Earth's moon? Most emphatically, no. Why don't they look like the Earth's moon? Okay? Eli's saying, well, the thing that's clear is that these are not spherical in shape. They don't have enough mass for gravity to have formed them into a spherical shape. They must have come from something different overall. The theory for the Earth's moon, which I don't believe I talked about, I don't know how that happened, is that the Earth had a very major impact. Now, we've talked about major impacts. That's what's believed to have caused Venus to rotate very slowly backward, Uranus to be on its side. Well, we believe that the Earth also had a very big impact. That's probably why we're tilted 23.5 degrees. And that big impact took a whole lot of the Earth's crust and mantle and blew it out away from the Earth. So the Earth would have had all of this material out there orbiting. The Earth would have had rain. But there's so much material in that rain that gravity started to make it clump together and form the moon. Now that is the conclusion. You don't come to a scientific conclusion without having some evidence, right? So what's their evidence? What made them come to that conclusion? they noticed that the isotopic abundance, that's the abundance of the different types of isotopes of atoms, was very similar to that on Earth. And they said, if the moon formed somewhere else or formed differently, it should be more different. So it's so close, it must be the same material that the Earth is made from. And so that's a big part of the reason why they think it's the impact hypothesis. I call it a hypothesis because that's really what it is. It's not a well-tested, known. It's the best guess at this point. So there are other hypotheses that could be there. For instance, the moon could have formed somewhere else and just migrated and been captured. The isotopic abundance suggests to me that's not the case. The moon could have formed at the same time as the Earth, just orbiting it the entire time. It's possible. Seems unlikely. Phobos and Deimos, on the other hand, are believed to be captured asteroids. Asteroids got too close, gravity of Mars captured them. I'm sitting here lecturing, and out of the corner of my eye, I see activity in my office, which had me worried. That's my wife and son, so we're all good, in case you guys are also disturbed by that. Okay, back to asteroids. We saw Ida and Dactyl. Why? Because one was orbiting, well, they're orbiting each other. These are the majority asteroids. You have Ceres, that is the dominant asteroid. Ceres is 33% of the entire mass of the asteroid belt. It's 1/3 of the asteroid belt, right there. And then 9% is Vesta. So those are the two major asteroids in the asteroid belt. You go from there, they get much smaller. Now, if you look at Ceres, Ceres is in the shape of a sphere. It has enough mass that gravity formed it into a sphere. Vesta, on the other hand, not so much. Both of them, you can see, have pock marks. They've had, what would that indicate? Collisions, right? So they've had collisions with things. You can see the evidence. Old surfaces, clearly no atmosphere or liquids on the surface to cause the slow surface evolution. So any damage that's done is going to be there until more damage is done to cover it up. So here is an unusual feature on Ceres. That light stuff is what's unusual. I mean, you see lots of impact craters, right? And so you say, well, that could be an impact crater, but what's that light stuff? It's believed to be a salt deposit in the crater. Now to meteor impacts. I have another meteor impact picture way further in the lecture than this. I didn't do a good job keeping these together. The picture on the left comes from Russia. What was it, 5 years ago or so? Do you guys remember that? Maybe, maybe not. The one on the left, or right, excuse me, also comes from Russia, but that was in 1908 or so. So this one here is the one that's called the Tunguska event, and this one, okay, I can't pronounce it. There is no. Okay. Apparently, it's not going to follow the link. I will do it manually. Except for I think that's going to stop the recording. Okay, that's been 2013. I said 5 years ago, right? Yeah. Lucky guess. So play Sesame. Okay. That was not it. That's what you call bogus. I went too far. Come on. Did I hit skip to the end?
No, I mean it was like skip to the end. So video.
It does look like it. I'm just going to try a different one, since I don't remember what the link was for the one I had done. This time I'll wait until it's gone through its startup and then make it full screen maybe. Imagine how astonishing that would be. Yeah. That sound is because it's going faster than the speed of sound, breaking the sound barrier, sonic booms. If I saw that happen, I'd be totally freaking out. I'd be like, it's the Americans bombing us, right? Well, you guys didn't grow up in the Cold War. I did. Yeah. We get some good Russian music coming on here. It's
cool.
Once again, I would be like, "Did you see that?" All these just different angles of people who happen to catch it. Mostly you can tell with the dash cams. And I'm going to go ahead and stop here because you could go on forever and have cool stuff. But we have to get on with the lecture.
Did it hit the Earth?
Yes, well, no, I take that back. They did not find any fragments that actually made it to the Earth. They were clearly in the Earth's atmosphere, but I believe they found no fragments in the Earth. Likewise with that Tunguska event, now that was in like 1908. Yeah, pretty historic as far as you're concerned. Question?
At the end of the video, it looked like it exploded.
Yeah, it exploded in the air. It fractured into smaller pieces and small pieces because they do get hot. And there's a lot of air resistance. The Tunguska one, says the impact site, but they've never actually found the site. What they have is a big region where they believe there was an explosion in the air that caused the quote impact site on the ground. I was going to show a bigger picture. It's just a bunch of trees knocked over because major explosion. This is the one that's a little scary. This is showing the asteroids again, but now it's showing their orbit. The video is still running in the background. Nice call. I should have known better than to have left it running. There we go. Stop. That did scare me. Okay, but this is startling nonetheless. If you look at the paths of the orbits of these asteroids, what would make this startling and a little scary? Yeah, a lot of those are crossing the Earth's orbit, aren't they? Yeah. The other picture, they're mostly out there between Mars and Jupiter. Fine, let them be. Well, there's a lot of these that cross the Earth's orbit. So that means that we have to be aware that it's possible that we will have an impact, a major impact with an asteroid. And so, like if you go to space weather, you will find places where they track these potentially hazardous asteroids, PHAs for short. And they track their orbits as carefully as they can, predict how close they should come to Earth in the future. They're not perfect predictions, but they at least give you an idea so that, if there's a doomsday event coming, we might be prepared. Although, what would we do in preparation? There were a bunch of movies that came out 5 or 6 years, actually maybe more like 10 years ago now. Like 2 movies in the same year, like, come on, doesn't they have an original idea? Where they were trying to stop an impact with an asteroid. And of course, the best idea is to go up there and use a nuke to blow it apart and have the 2 pieces split going into the side of the Earth, right? Isn't that awesome? You make that happen. You get sort of like Bruce Willis, who's a master at mining asteroids, to go up there, Anyway, that is something that people really do worry about. Not much that we can do about it at this point, but maybe we can develop technology to protect us. What do we have to protect us right now? The atmosphere. That's what we have. And it does protect us from a lot. I believe it's on average once a month, a house-sized object comes into the Earth's atmosphere. And yet they very rarely hit the Earth. So rarely, I told you I have my order is really out of whack. Later on, I have a picture of a car that has a hole in the seat where an asteroid went through, a meteorite at that point, went through it. There was a story from India 2 years ago about a person who was killed by an asteroid, which would be the first ever documented case. But it turned out the astronomer said, no, it doesn't match anything that would go along with the story. It was a conventional bomb, basically. Okay, so comets. First and foremost, okay, I know this is silly, but I'm pedantic on many things, and here's one of them. How do you pronounce that comet? Get ready for me to say no.
Halley?
People say Halley's Comet. Why? Because there was a musician whose last name was Halley, and now I can't remember his first name for some reason. But the name of his band then was the Comets, so it was Halley and the Comets. But this is named after a guy who most people agree name should be pronounced so it rhymes with Halley. So it's Halley's Comet. Important, right? Just so you can go out there and say Halley's Comet, everyone will look at you funny, and then you can be smug and know, yeah, you just are ignorant. Okay, so Halley's Comet, why is it named Halley? Because the person who predicted it, who recognized the pattern, predicted it would be coming back again, was named, I can't remember his first name, Edward or something like that, Halley. Somebody actually took the time, by the way, to go and poll people in England with the last name that's spelled this way. 89% pronounced it Halley, which is the way that we believe he did. There were a few that pronounced it Haley. Well, actually, I think there's only one that they found that pronounced it Haley, and some that pronounced it Holly. Okay, so back to this. Comets come back on very predicted schedule. Why? Well, same reason the Earth has a very predicted schedule. Its orbit around the sun. These comets are orbiting the sun. What's different about these comets' orbit and our orbit is that they have a very eccentric orbit. Their orbit, if it's eccentric, what does that mean?
Out of the ordinary.
Out of the ordinary, right. So the eccentric orbit is a non-ordinary orbit. It's not circular, it's stretched. And comets have very eccentric orbits. If you look at this picture here, you probably noticed that's a pretty eccentric orbit right there. Not close to circular. Because it's very eccentric, it comes really close to the sun. Remember, the sun is at one of the two focal points. The more you stretch it, the closer it's going to get to it. And using Kepler's law, since these are all orbiting the sun, all of them are going to obey the relationship that period and year squared is equal to the average radius in astronomical units cubed. So the average radius is just you take this distance plus this distance and divide by 2. Well, if it comes really close to the sun, you basically take that farthest distance and divide by 2, and that's your average radius. For the comets, they're like this shape, but coming from much further away. So coming from much further away, right? They're all coming from beyond the orbit of Neptune. So that means that their period of recurrence is going to be, somewhere in the ballpark of the period of Neptune. I say somewhere in the ballpark. If it went just out to Neptune and in, its average radius would be half of Neptune's radius. If it goes farther, speed further. So these things have long periods because their average distance from the sun is very far, even though they get really close. So as they're orbiting, remember we learned from Kepler's second law that they go faster when they're closer and slower when they're farther away. So if you just take this picture here, it's going to be just inching along when it's out here at the place that's called apogee. I started to write P because I was thinking of the next one. Apogee, or if you want to be specific to the sun, it's aphelion. And they're really screaming when they're here at perigee. Or once again, if you want to be specific to the sun, perihelion. Perigee and apogee would apply any orbit. Perihelion and aphelion would apply to something orbiting the sun. Perigee is the closest it gets to the star. Apogee is the farthest it gets from the star. So when comets come, when they're far out there, of course, what's the temperature like out there? Okay, Mira, I'm just going to assume you said it right because I couldn't hear what you said. It's cold. It's really cold out there. So the icy comets are just chilling. But when they come in close to the sun, the temperature rises. When the temperature rises, they start to sublime. That is, the ice goes into gas. And when the ice goes into gas, then you start having clouds of gas leading, and you start having stuff that the sun will then scatter off of that we see as the tails. And of course, what's happening to the comet when it has a tail, when it has stuff subliming? It's losing mass. So the comets can only last so many times around the sun before they're just going to be used up, no longer there. Well, what happens to the material when it gets vaporized? It becomes the tail, but then that stuff just forms a cloud of debris, which is what leads us into our meteor showers, which I suppose there was one this past weekend I could go out and observe. Okay, moving forward then. Here's another picture of Halley's Comet. Not as pretty a picture. Here is another picture. This is the same comet. Now you can see something going on here. You can see that there is an object that gas is coming off of. How cool is it that we have pictures like this? Right? Instead of just seeing something in the sky that from night to night you can see is slowly moving. I don't know if you've watched like A Walk to Remember, but don't be fooled. The comets, you don't look out in a telescope and see it moving. Sure, they're moving just like the planets are moving, but you can't look in the telescope and see them moving. You periodically have to adjust your telescope because it did move. Also, just for the record, in case you believe there was something that made sense at all in A Walk to Remember, telescopes are not good instruments for viewing a comet. They're not good instruments for viewing a comet because the comet tail is generally large, bigger than the size of the moon, by quite a bit usually. So the best thing for observing a comet is just a pair of binoculars. That's good for comet viewing. Okay, let's get back. I keep thinking of things to correct in A Walk to Remember, but most of you probably haven't even seen it, right? What's the point of correcting something you haven't seen? So here is a diagram showing the anatomy. I meant to put anatomy here, and I just couldn't think of that word when I was making the slide. Anatomy of a comet. So you have the nucleus. The nucleus is the chunk of ice and rock. And when you get close enough to the sun for things to happen interesting, then you're going to have the coma, which is the gas right around it. You have the head of the comet. By the way, the name comet comes from its shape like a comma. You have the head of the comet out here, and then you have the two tails, the dust tail and the ion tail. The ion tail is pointing directly away from the sun. So you see in this picture, to the sun is this way, and the ion tail is directly away. Why? Because the ion tail is charged particles. The sun is blowing away charged particles. So there's an interaction between the charged particles that causes it to be strongly affected by the solar wind. The dust tail is also affected by the solar wind, so it's pushed back somewhat in the same direction as the ion tail, but it doesn't interact nearly as strongly, so it doesn't just line up. So here's a picture showing a comet coming in, and you see that the tail, this one here, it only shows apparently the dust tail because it's not pointing directly away from the sun. Either that or it was just bad artistry. Probably mostly bad artistry, just like my straight lines here are failing. So you can see the direction of the tail is not telling you the direction the comet is traveling. It's telling you where the sun is. And you see you have an arrow that shows this tail is going away from the sun, and it's leading. The tail is ahead of it. Happens because the sun is blowing the tail away. So here's some good pictures of the tail. Here's the sun. You see once again, the gas tail straight. The dust tail is off to the side, but notice that it's close to the direction away from the sun. It's not trailing behind. Right? If there was no solar wind, it'd be where I drew that. How do you take a picture like this? This is a picture of the nucleus of a comet. On the picture on your right, B, down in the lower corner, that's actually the foot of the lander that landed on the comet to take the picture. That's not part of the comet. It's not signs of intelligent life living on the comet. So how do they take a picture like this? Well, clearly they landed on, because they just talked about a lander. They're far enough away from the sun that it's not blowing stuff everywhere. If they were close enough to the sun, there would be so much wind from stuff being blown off of this as it is heated that you would have real difficulty. But here you can see what the comet nucleus actually looks like there, what you have in the core, which is, I think, totally cool. This is done by the Russians. Here you can see a little bit of stuff blowing off in this picture. Here you have a jet, a place where it's heated up and stuff is blowing out. Here's another, you can see a little bit there. You probably can't see it at all up there, but I can see it on the screen here. So you have gas jetting out of that material. Before I go on, I just have to talk about fun stuff, right? We're in astronomy class. What is in the tail of a comet? It's probably going to be the gases that are frozen on the comet. And through spectral analysis, they determined back around 1900 that Halley's Comet had some cyanide gas in its tail. And when Halley's Comet came by, I think it was like 1911, it was positioned and came close enough to Earth that the Earth actually passed through the tail, which is pretty cool, right? People were really worried. We're going to pass through the cyanide-containing tail of this comet. Conclusion? We're all going to die. People really were concerned. Some brilliant, dishonest people sold pills that you could take that would make you immune to the cyanide gas. Brilliant, because if it fails, you know what? You're dead. So you can't come after them. And if you don't die, how do you know that the pill didn't work? Right? It was a no-lose proposition for the people who sold them. But of course, there was no problem. Why would there be no problem? The atmosphere. The Earth has this little thing we like to call an atmosphere. And so anyway, it was no problem whatsoever. Now, Chiron here is a centaur. And what is a centaur? A centaur is an object that's orbiting the sun that is like like let's say Neptune or like a comet, but that does not go past Neptune. And so Chiron is an example. It comes by every 50 years, and its closest approach is inside the orbit of Saturn. It doesn't quite make it to Earth. Not such a bummer. We wouldn't want. I'm sure it's in a tidal locking, so we don't have a problem. But you do have comets and asteroids that will periodically get too close and get torn up. So this one's very famous, the comet Shoemaker-Levy. Shoemaker and Levy are two dudes who discovered this comet. They're given co-credit for it. And this comet got too close to Jupiter. And once you get inside of the Roche limit, I've talked about that before, so that's why I just say the word here. The tidal forces are so strong. I think I have it right. The tidal forces are so strong that it will tear something apart if it's held together by gravity. If it's bonded together, if it's cemented together, it can last closer. But if it's just held together by gravity, it'll be torn apart. And so this comet got too close to Jupiter and was torn apart. So we had very practical explanation. Hey, we're right. That is what's going to happen. And then the pieces crashed into Jupiter. And so there's lots of impacts that occurred with Jupiter, creating huge explosions that would have annihilated life on Earth, but did really nothing to Jupiter. So here's a picture of the, quote, surface. Remember, there is no actual surface, but the clouds that we see as the surface of Jupiter after, wow, and you really can't see that nearly as well. It's better there without the lights. That's what you had after the impact of one of the pieces that had been shredded from Shoemaker-Levy 9. So we have a real-life example of stuff being torn up and falling into the planet. Fireballs. Fireballs are cool. That picture, the video we saw from Russia, that would clearly be called a fireball. Fireballs occur when you have bigger things going through the atmosphere, not just little size of a grain of sand. And so this is a picture showing a fireball from 2014. I talked in class on Friday about the meteor showers that looks like they come from one location, which is called the radiant, because it looks like it's radiating from that location. And it's the direction the Earth is traveling. This picture here of the railroad tracks is to help you understand why it looks like they're coming from one location. The railroad tracks, as you go farther away, they appear closer, right? They're not really closer. They're staying the same gauge the whole way. But because of our perspective, they appear closer. It's the same thing, those meteors, very far away, you're talking the entire atmosphere that they're hitting, but it looks like they're closer and then getting farther apart as they pass by us. So that's why the meteor tracks appear to come from one general location, which is the direction the Earth is traveling at the time of the meteor shower. Now, Eli and I got into some discussion. He looked stuff up during class or at the end of last class period about the 1833, that was what he looked up, was when it occurred, meteor shower. That picture on the left is one that should be familiar to most advocates. It's the one that we show in all of our literature for the day the stars fell. It's I can't remember who did it, Adolf something or other, but it's a picture depicting what was going on. The one in the middle is another picture that somebody drew of, what they thought it should have looked like. In reality, there were nowhere near that many visible at one time. The article on the right is one to verify the date. This was published on Wednesday, November 13, 1833, and you see there the first line, this morning about 3 or 4 o'clock, a most remarkable meteor phenomenon was witnessed. So that is a meteor shower. The Earth was passing through a cloud of dust left behind by a comet. every November. It's coming up in what, a month? We have the Perseid meteor shower. And this year, the Perseids, I think, are supposed to reach their climax on like November 18th. So during Thanksgiving break, the first weekend of Thanksgiving break, is when it will reach its climax. Is it going to look like this? No. It'll look a lot more like that. Now, this is a 20-second exposure, right? It's not a long exposure, but you only see one meteor in that 20-second exposure. You don't see lots of meteors at any one time. Remember, meteor is the light you see in the sky. What do you call it if it hits the ground? Meteorite. So here is a meteorite. Now this one here has a fun story to it. This is the Willamette meteorite. It's from your textbook. This was found in the Willamette Valley in Oregon. There is no impact crater there. Now that's huge. On the next screen, we'll show I think on the next slide, I have a picture of the biggest chunk they found from the Behringer meteor crater in Flagstaff, Arizona. The thing's only about this big. You can see here that is a lot bigger. It's huge, and yet they found no impact crater. We're scientists here. We have a scientific method. We've got this big thing that's pretty clearly a meteorite. Right? That's not how they look on Earth rocks. How does it get there without having an impact crater?
Like the water.
Okay, that is the conclusion. I don't know how much you guys have studied geology, but the understanding that scientists have is that during the ice ages, that you had Lake Missoula, this huge lake behind an ice dam. And then the ice dam burst, and you had enormous flooding of Washington, Montana, Oregon. And they believe that during that flooding, this must have been transported down from somewhere up in Canada where it must have hit. Now, is there any evidence that that's what happened? No, that's a hypothesis that makes some sense, but there's really no evidence to support it. It's an idea. Well, what's the story behind this that makes it interesting? This notice here, it says it was, quote, discovered, end quote, by an enterprising local farmer in 1902. The story is better than what they have there. This farmer discovered it on the adjoining property to his farm. Now, it says discovered because it was well known and actually a sacred place for the Indians. But he discovered it. It was on property actually owned, oddly enough, by an iron and mineral company. And so he spent 90 days working really hard to move the 3/4 miles from that property onto his farm. And then he claimed, hey, I found this on my farm. It says here that he proceeded to steal it and put it on display. Maybe he put it on display, but he was sued and they took it back. Because there was plenty of pre-existing knowledge about the meteor and where it was located. It wasn't on his farm initially. But it's very large. That's why the picture's here. Oh, in between, that little rock in the bottom left is what drilled the hole through that car seat. If you had been sitting on that car seat, it would have been fatal, obviously. But nobody was. No harm, no foul. Here in the center is the meteor from the Behringer meteor crater, or meteorite, excuse me. The first time I went to visit the Behringer meteor crater, the tour guide said, and if you can lift it, you can keep it. Or yes, he said, as if you can carry out your car and keep it. And they encouraged us to try to lift it. And so I got down there, and I moved it a little, but I couldn't actually lift it. And then my buddy I was with, he was able to do the same. I think that must have worried them, because the second time I came to visit, there was, you can't touch it. It is very heavy because it's made out of essentially iron and nickel, which are dense materials. So it's heavier than you would expect by looking at it. If you look at these, you see that there are different types of meteorites. This is clearly metallic. I'm just going to leave it as metal. That way we don't have to worry about if it's got 2 L's or 1. This one here has got some funky things in it, right? It's called carbonaceous. It has, just like the carbonaceous asteroids, the C-types, it has the carbon compounds in it. And then the one on the right has some interesting minerals in it that make it look prettier. The meteorites come in chondrites, achondrites, carbonaceous chondrites, and metal. And the difference, chondrules are little rocks, if you will, cylindrical rocks. And the ones that have the chondrules are believed to have never been heated up enough to melt those things, whereas the achondrites have been heated up and have had them melted. Anyway, moving on. I am going to finish today's lecture. Where did the comets come from? We have lots of questions. We've answered the most important one, where are the ice giants? But now we're asking, where did the comets come from? Where did I say their home was? Where?
Outside the orbit of Neptune.
Okay, outside the orbit of Neptune. That's right. Now, it turns out there are two locations for comets. One is, and I've mentioned these before, but now we remind you so that it sticks in your brain better. We have the Kuiper Belt. The Kuiper Belt is in the plane of the solar system. That's the plane that the planets are orbiting. And it is basically out beyond Neptune in that plane. Then we have the Oort cloud, which is a spherical shell that is much farther out. So we have two locations that comets come from. One is the Kuiper Belt, which is in the plane of the solar system and just beyond Neptune. One is the Oort cloud that is all around the solar system and much farther out than the Kuiper Belt. How do we even have predictions of these? I mentioned when I first brought this up, which was probably like the first week of school actually, that when I started teaching astronomy, they really had no confirmation of either the Kuiper Belt or the Oort cloud. They had a few objects they thought were Kuiper Belt objects, but they couldn't see them out there. Well, now they've mapped literally thousands of Kuiper Belt objects and a few Oort cloud objects as well. But before they mapped them, how did they know they were there? Right? By mapping, they tracked them with telescopes. They knew they were there by looking at comets. They had noted that all of the comets that come in the plane of the solar system had relatively short times that they came around. Like 50 years or so, 100 years. The ones that came at crazy angles instead of being in the plane had much longer periods, much longer time before they returned. Much longer time before they returned, according to Kepler's third law, means that they're farther out there. You can take the time that it takes for them to return their period and calculate their semi-major axis, their average radius, double that and say they must be coming from that far away. And so that's how Oort was able to predict there's a cloud that's spherical in shape because they're coming in all directions from really far out there. And Kuiper was able to say there is a belt that's closer in by looking at the comets. Oh, I didn't stay on this slide long enough. So the solar nebula theory said that we had a big cloud of gas. Shockwave hit it, started to condense. Because of rotation, it flattened out. And you have all of the debris shown there. The stuff that is in the Kuiper Belt is just the outer portion of this disk. The stuff in the Oort cloud is stuff that had clumped before it collapsed down. Once it clumped, it stayed in its orbit instead of having collisions bring it into the flat plane. And so the Oort cloud should be earlier clumping material. This here goes back to why we have rocky planets and Jovian planets. It's here at this point to help us understand why we have the Kuiper Belt and the Oort cloud. So we have the temperature during formation of the solar system as a function of distance. Now, you should be very aware I said as a function of distance? Not really. Clearly, the distance from the sun to Mercury is small compared to the distance of the sun to Venus and Earth. This is not a to scale distance. This is simply placing them by what the temperature was. And so the temperature for Mercury here was, if I followed that down right, about 1,200 kelvins. And at 1,200 kelvins, the number of things that can stick together, things that can melt, is pretty much limited to Al2O3, corundum, otherwise known as sapphire if it's a single crystal, and iron. So Mercury, those should be the primary elements on Mercury because those are the only things that were actually able to stick together at the temperature where Mercury was formed. Now, if you go further out to where Venus and the Earth were formed, so we'll come out here to, that's not straight down for sure. There's Earth. Earth can hold on to things like iron oxide, otherwise known as rust, olivine, and other silicate minerals. So we have lots of these silicate minerals in the Earth. Silicon dioxide is what quartz is. Quartz is a single crystal silicon dioxide. So the Earth is largely silicate minerals, quartz-based things, along with iron. You go further out still, you see Mars. Mars could hold on to some, that was asteroid belt. Mars could hold on to pretty much the same stuff as Earth, maybe a little bit of the volatiles. You get out to Jupiter, though. Jupiter can hold on to hydrated minerals, and then you go to the rest of these, and they can hold on to pretty much anything. And so the stuff out there, the gas giants, is where it was cold enough that things could clump together that were like water, and thus could hold on to them. Well, the location where notice this is absolute zero here. Nothing can be to the right of that. That's as far as you can go to the right. But your Oort cloud is spelled O-O-R-T, and Kuiper belt are out there at the very edge, very close to zero. And so any kind of gas would stick together. And so that's how you get these ice balls. It's not just water ice. It's ammonia ice and methane ice, other kinds of ices. I finished 2 minutes early. I'm proud of how fast I went today.